And in exercise 13, they say a 70 kilogram base runner begins his slide into second base when he's moving at the speed of 4 meters per second. The coefficient of friction between his road and the earth is equal to 70. He slides so that his speed is zero just as he reaches the base. So, how much mechanical energy is lost due to friction acting on the roller? How far does it slide? So, this is a problem now about basically energy. So, this is a problem of energy involving the action of a non-conservative force because we have to calculate how much mechanical energy is lost due to friction. So the friction is doing a work. That work is work of a non-conservative force because the friction is a non-conservative force. Remember the definition of non-conservative force. A non-conservative force, when you go from point A to point B to different path, the amount of work done is different. For a conservative force, when you go from point A to point B to a different path, the amount of work done is the same. Friction is a non-conservative force. So there will be a loss of energy due to the friction, and a loss of mechanical energy. And that energy really, is not destroyed. That energy is being transferred, it's being converted into other forms of energy. So, for example, there could be, remember always, generation of thermal energy. There is sound generation, right? And all these are forms of energy, right? So, let's see the problem. We have basically here this base ruler. So this is the ground, the field where they play baseball. Here is the base. That is the ultimate goal of the base ruler to reach the base. Right? And then the base ruler starts here sliding. He begins his slide into second base. And when he's at this point where he begins his slide, he has a speed that we're going to call initial speed of 4.0 meters per second. He's going to slide all this distance until it reaches the base. And when it reaches the base, now his speed is 0 meters per second. We know that there is a coefficient of friction that is kinetic friction, so there is a coefficient is K between the growth of the base ruler and the earth that is equal to 0.70. Remember, we have coefficient of kinetic friction and coefficient of friction. This is a coefficient of kinetic friction because it's sliding, it's moving. And the first we have to do is to calculate how much mechanical energy is lost to the friction. Well, the first that we are going to do here is to calculate, the variation of kinetic energy. Because remember the work energy theorem that said that the work is equal to the variation of kinetic energy. So this is work done by the force of friction. This is work that is done by an external force. So the work done by the external force, that is the force of friction, there is a force that is acting on the base ruler as it's moving. No, there's a force here, that is the force of friction kinetic, that at against the motion. Remember that this guy is moving to the right. Is moving toward base, but the force of friction is acting against the motion. So this force of friction is doing a work, and that work can be calculated as the variation in kinetic energy. And this is what we call the work energy theorem. So I can say then that this work is equal to kinetic energy final minus kinetic energy initial. So we know that the kinetic energy final is 1/2 mass B final square minus 1/2 mass B initial square. We know that the final speed when you reach the base is 0. So this term will be 0 because the B final is 0, so the kinetic energy final is 0. So we're going to have that the work is equal to minus 1/2 mass is 0 squared. And then the work be minus 1/2. What is the mass of this person? The mass of the person is given here, 70 kilograms. Times the initial speed squared, so 4.0 meters per second squared. So we get that the work is negative, when we calculate that, negative 560 joules. This work is basically the work done by the external force of friction. Seems this work, cause a decrease in the energy of the system, because we go from kinetic energy that is different from 0 to kinetic energy that is equal to 0. So there is a decrease in kinetic energy, so this work is negative. So this is the work done by the external force friction. So how much mechanical energy is lost due to friction acting on the runner? Well, the mechanical energy that is lost due to the friction on the runner is 560 joules. That is basically the work that was done by, this force of friction. Now, the next thing they want just to find is how far does he slide? How far does he slide? Well, we're going to do the second part of this problem. First, we need to know what is the magnitude of the force of friction that acts on this person. Because with that force of friction, we'll be able to calculate the acceleration or deceleration as he's sliding toward base. Because his velocity is decreasing, so that means that there is a deceleration of motion. It's a deceleration. So instead of having, a positive acceleration here, we have just basically a negative acceleration or deceleration. So I will just look at the person again. He's here at the very beginning, but he starts sliding. Then he has some mass, so he has also some weight. So the weight of this person the product of the mass times the gravity. So it's 70 kilograms times 9.8 meters per second square. So the weight of this person is 686 newtons. Now, we also have then a normal force. It's acting upward. So this is the normal force. The normal force is always acting perpendicular to the surface. So the normal force is antiparallel with the weight and have the same magnitude than the weight. So we know that in this case, the normal force, if the weight is a force of 686 Newton pointing downward, the normal force is a force of 686 newtons pointing downward. 686 newtons pointing downward. So remember, you can get these from the sum of forces in y, making this equal to 0 because of course there is no force in y, so you say normal force minus the weight equals 0, so the normal force equals the weight. And that's why I said, that the vector normal force is 686 newtons over. Now, once you know the normal force, you can calculate the force of friction kinetic. Because the force of friction kinetic is mu sub k times the normal force. If the coefficient of kinetic friction times the normal force. So the force of friction kinetic is what is mu sub k 0.70 times the normal force, that is 686 newtons. So the force of friction kinetic would be, we calculated 480.2 newtons. So I would say that it is just approximately 480 newtons. This is the force of friction kinetic. With the force of friction kinetic, now I can calculate the acceleration, right? Because we have, due to the action of the force of friction kinetic, we know that the velocity of the person is this, but as there is a decrease in velocity, the vector delta v points to the left. The variation of velocity is a vector that points to the left, and the acceleration vector also points to the left. Right? If the velocity is pointing to the right, if the guy is just sliding toward the base that is at the right. So this acceleration is the portion of the force of friction kinetic, that is the external force acting here, divided by the mass of the person. So it's just 480 newtons divided by the mass of the person, that is 70 kilograms. So the acceleration would be approximately like a 6.86 meters per second square. That would be the acceleration. And this acceleration is going to be negative because it's a deceleration. And it's deceleration because the velocity is decreasing. Now, once we know the magnitude of the acceleration, Now we go again over the equations of the kinematics, and we say B final square is equals B initial square plus 2A delta x. Because what we want to calculate, how far does he slide? How far does he slide is the variation in position, right? With the distance that he travels, when he's sliding, delta x. I know that this final speed is 0. So we get that 0 is equals to B initial square. The acceleration now I know is negative because it's against the motion. So we say minus 2A delta x. So subtracting B sub 0 square from both sides, we get negative B sub 0 square equals negative 2A delta x. And then dividing by negative 2A delta x, we get negative B sub 0 square over negative 2A equals delta x. So delta x will be the a square, of course, negative for negative to be positive, and then it's the square of the initial velocity. So it's 4.0 meters per second squared over 2 times the acceleration to the force of friction, that is in this case a deceleration. Deceleration, sorry, just misspelled deceleration, right? So this is 2 times the acceleration, there is 6.86 meters per second squared. So when you calculate delta x, this delta x will be approximately 1.17 meters, which is approximately 1.2 meters. So from his slides, he draws, basically 1.2 meters. How far? But as he slide, 1.2 meters. So this is a very, very, very interesting exercise where we use the concept of kinetic energy, variation of kinetic energy, and relation to the work of external forces with the kinetic energy. So the energy theorem, work energy theorem. We use about the concept of the force of friction and how the force of friction is calculated based on the value of the coefficient of kinetic friction and the normal force. In this case, because it's kinetic friction, and also we use again one more time the equations of the kinematics. One more time the equations of the kinematics. So it's a really, really very interesting exercise in this case. Let's solve one more exercise before taking a break. Let's solve this exercise here about energy. There is exercise number 29 of your book. We say that a 50 kilograms projectile is fired at an angle of 30 degrees above the horizontal with an initial speed of 1.20 times 10 to the second meters per second. From the top of the cliff, it is 142 meters above the ground, where the ground is taken to be 0. So they say, what is the initial total mechanical energy of the projectile? Suppose the projectile is traveling at 85 meters per second at its maximum height of 1,427 meters. How much work has been done on the projectile by the air friction? The air friction is a resistive force, right? So now we're considering that there is an effect of the air on the projectile, which is actually because there is an effect of the air surrounding us projectile when it's fired or it's flying. And then they say what is the speed of the projectile immediately before it hit the ground. If the air friction does 1.5 times more short than the projectile when it is going down as it did when it was going up. So if we increase the air friction in 1.5 times, right, which is 1.5 times. So let's see what we have here. So basically, let us just make a sketch. Always these sketches are very helpful. We have here the curve, and this is y equals 0, where we have the ground. Now we are firing the projectile from the cliff, and it's fired at an angle of 30 degrees. With respect to the horizontal, and you have an initial speed equals to with respect to the horizontal, and you have an initial speed equals to 1.20 times 10 to the second meters per second, so it's going to be 120 meters per second, basically. Now, what else we know? We know that the height is 142 meters. So from the top of the cliff to the level ground. This is Y or H. So what is the mechanical energy of the projectile at the top of the cliff? Let us call that mechanical energy initial. When the projectile is fired. So this mechanical energy initial is equal to the gravitational potential energy initial plus the kinetic energy initial. So this gravitational potential initial will be mass times gravity times the initial height, which is going to be y or h, is 142 meters, plus the kinetic energy initial, that is equal to mass the square of the initial speed. We know the mass of the projectile is a 50 kilogram projectile, so we say that mechanical energy initial is equal to mass 50 kilograms times the gravity, 9.8 meters per second squared, times y, 142 meters, plus, then we have the kinetic energy, that is 102, the mass, that is again 50 kilograms. Let me just make a quick correction here. We say 50.0 kilograms, which is the same as 50. We change it to the years. So we say 50.0 kilograms. So 1 over 2, 50.0 kilograms times the square of the speed. This is 120 meters per second squared. So if we calculate the magnitude of the mechanical energy, this mechanical energy initial would be 4.30 times 10 to the 5 joules. So this mechanical energy initial is given by the gravitational potential energy due to the position at the top of the cliff and above the ground of this projectile, plus the kinetic energy initial, and the kinetic energy due to the initial speed of the projectile is fire. In the second part, they say suppose the projectile is traveling at 85 meters per second and its maximum height of y equals 457 meters. So how much work has been done on the projectile by deflection? So basically what they say in this part 2 is, okay, the projectile have gone now from this position at the top of the cliff, where it was fire, right? And then, it has here this initial velocity of 120 meters per second. We follow a parabolic trajectory. Eventually, it reaches this point that is the highest point of the trajectory. And when you measure the height of this point with respect to the ground, let's call this the final, final, or H final. This is now 427 meters. And now the projectile at this maximum height have a velocity that is horizontal, and its velocity here, we're going to call V final, is now 85 meters per second. So what happens, there is a new mechanical energy here. That is the mechanical energy 2, or mechanical energy final. And that mechanical energy final will be given by this new height, so the gravitational potential energy at this point is the height, and the kinetic energy at this point will do the new velocity. So basically now I know that if I want to calculate, because basically what we want to calculate really here is the work that was done by the air, by the friction between the air. So this is a non-conservative force. So I would say that in this case, if I want to calculate this work, then it's going to be a negative work, of course. We say that this work of the non-conservative force is equal to the variation in the mechanical energy, right? So it's equal to the mechanical energy final minus the mechanical energy initial. So we already know the mechanical energy initial, so we can say that this work of the non-conservative force, or the work of friction, is the mechanical energy final. It will be the gravitational potential energy final, be the gravitational potential energy final plus the kinetic energy final minus. We know the mechanical energy initial, that is 4.30 times 10 to the 5th joules. I have to calculate this now. So the gravitational potential energy final would be the mass 70 kilograms. No, sorry, 50 kilograms. Sorry. These 50 kilograms is the mass times the gravity, 9.8 meters per second squared, times the new height, that is 427 meters, plus machinery in the final that is 1 over 2, the mass of 50 kilograms times the speed at that point, that is 85 meters per second squared. Minus the 4.30 times 10 to the 5th. So when you do those calculations, you're going to get that this is 3.90 mechanical energy final, 3.90 times 10 to the 5th joules minus 4.30 times 10 to the 5th joule. So this would be minus 0.40 times 10 to the 5th joules, or minus 4.0 times 10 to the 4. That is just the difference in mechanical energy between the 2 points, the top of the cliff and the top of the trajectory, and that difference in mechanical energy is due to the action of one resistive force, that was the resistive force of the air, and so it's considered work of a non-conservative force. Finally, they are asking what is the speed of the projectile immediately before it hits the ground. If the air friction does 1.5 times as much work on the projectile when it's going down as it did when it's going up. So, well, we know that the mechanical energy initial will be equal to, in this case, we can say that is equal to, the mechanical energy final plus the work done by the non-conservative force. If we take this work positive, right? We are taking the work positive. We can say that it's mechanical energy final plus the work of the non-conservative force. I will be taking this work positive to say, okay, I know that if I add the work that was done by the non-conservative force with the mechanical energy that we had at the end, right, as the work of non-conservative force is just the amount of energy that was lost, if I add it to the mechanical energy final, I get the mechanical energy initial. So if I know this, but also if they say now the work when it's going down, this is the work when it's going down. If we know that this work of the non-conservative force when it's going down is 1.5, so 1.5 times as much work when it's going down than when it was going up, we can say this is the mechanical energy final plus 1.5 the work of the non-conservative force that we calculated. But remember, I will be putting this now positive, right? So I will say that this will be then now when I calculate this, of course, remember that we want to find the speed immediately before it's going to hit the ground. So immediately before that is going to hit the ground, we have no gravitational potential energy final, right? So what I have is just kinetic energy. All the gravitational potential energy was converted to kinetic energy. So I will say that this mechanical energy initial, right? That is basically the mechanical energy that we have at the this point, there is 3.9. It's 3.9 because now we're going from this point over here to hit on the ground. This is what the projectile is doing now. Hitting the ground again. So now is my mechanical energy initial. That mechanical energy initial now is 3.90 times 5 joules, right? So I can solve for mechanical energy final. And say mechanical energy initial minus 1.5 the work of the air resistance is going down. Sorry, the work of the air resistance is going up because it's 1.5 is the work is going down. Is equal to the mechanical energy final, but in this mechanical energy final we have the gravitational potential energy final is 0 because it's hitting the ground, so now at the ground level plus the kinetic energy final. So we can say that this mechanical energy initial minus 1.5 the work of the non-conservative force is equals to 1/2 the mass times that final velocity squared that we want to calculate. So I can now solve for the final velocity, so I can say that the square root of 2 times the mechanical energy initial minus 1.5 the work of the non-conservative force when it's going up over the mass is equals to the final. The final. This is solving for the final here. The final. This is solving for the final here. This is present. So we're going to get now that B final is the square root of 2 times, what is this mechanical energy initial? Is the mechanical energy at this point that we found here in the previous question, that is 3.90 times 10 to the 5 joules. Minus 1.5 times the work of the non-conservative force, that is 0.40 times 10 to the 5th. I would put that positive then. To the 5th joules, extend this curve. All these divided by the mass of the body, that is 50 kilograms. And if you calculate now B final, this B final would be, this is exactly, before hitting the ground, it would be 150 joules per second.